everyone, and welcome to week 2 of the Physics 8B live stream, fall 2025 edition. So this week we're going to continue working on electric fields. So the first 3-4 weeks of class are pretty much focused on electric fields. Last week we talked about point charges, the electric fields that they create, and the electric force between point charges. And this week we're moving to Gauss's law, which is a method to find the electric field created by things that are typically not point charges but do have a lot of symmetry. So that's the requirement to apply Gauss's law, and we'll talk about that. But just as a reminder, you can find this live stream and all the other live streams for that matter, along with all the homework problems and their solutions, at slackademia.com, and just go to the study guides page, and if you scroll down, there's a course that's called Physics 8B live stream. And it is a free course. It's just a container where I'm going to put all this stuff, and you don't have to enter credit card information. You don't have to do anything. Just sign up for free, and you can get access to the content. And so the goal is to have just one go-to place where all of this lives, just for out of convenience. And then if you need to get in touch, you can either use the contact form on the website, of course, or you can just get in touch through Facebook, facebook.com/MySlackAdemia. It's a good way to reach me. And speaking of that, for that matter, I got a few questions. Actually, I got one question a few times, enough times that we should talk about it, because it is an important point to cover in 8B. And as I said, I'll try to the important questions, or the interesting questions that I get, I try to include them in the next live stream. So this is one that we're going to talk about first, and then we'll move on to Gauss's law, and we'll see how it works in practice. So let's first address this important point of confusion. Now, I know that there are far more students that are confused about this than there are students that ask me about it, but that's okay. This is a confusion. At some point, you're going to bump into it if you haven't already. It's the difference between writing minus q versus writing q as negative in the case of a point charge. In fact, it also extends to any charge, but let's talk point charges because that's what we know for now. So what's the difference between minus q and q? Okay, well, it doesn't seem like there's much of a difference. I mean, you might argue, look, minus q is negative, right? So q negative, same thing. Like, what's the difference? Okay, well, there is quite a big difference, which is that in the first case here, the minus is out front. So if I'm trying to describe a negative point charge and I put the minus out front, it means that the letter q stands for a positive quantity, right? Q itself would be, let's say, 10 nanocoulomb, and the fact that there's a minus in front tells me that the charge is negative. Fair enough. Versus this, within the letter q, everything's built in. So you might have q itself is minus 10 nanocoulomb, meaning that when you see the letter q, you have to remember, oh, wait a minute, it's a negative quantity. Now, I don't like that. I think that this is very confusing. I think that this is a much better notation. But guess what? Nobody cares what I prefer, and there is no unified, notation for this in physics. You will encounter both, and that is where confusion arises. So let's go through it. Let's just real quick compare the two and see why there is confusion. Okay, so let's start with a negative point charge here. And I'll start with the first case, which is minus q. Okay, so q in and of itself is a positive quantity. And I have a minus out front that tells me that this is a negative point charge. And I'm going to have a location here, x naught. And I know that the electric field created by a negative charge, let's call it E minus, is going to point toward the point charge, like this. And I know that the r hat direction is the same as x hat in this case, right? So actually r hat is x hat. Coincidence? Well, not coincidence, just happens to be the case this time around. That's fine. Point is, that's the radially outward direction. Okay, so if I want to write E minus as a vector, right, I know what the electric field created by a point charge is. It's kq over r squared r hat. So if I plug it in, if I plug in k, the charge is minus q, divided by r hat is really x naught hat. X hat Well, then what do I get? I get minus kq over x naught squared x hat. Now, the nice thing about that is that this is a positive number because q in and of itself is a positive letter. There's a minus in front of q to indicate the charge is negative, but at least I can see my minus, it's out front. Okay, so this thing here is really magnitude, which, you know what, is what I would expect, because when I see a collection of letters and variables like this with, let's say, just this, right, with no negative sign within it or in front of it, then by definition I tend to assume it's a positive quantity. It's just out of habit, right? And then, you know, you can argue, well, that's magnitude, but okay, that's fine, because this, the minus, actually applies to x hat, and this is direction. Right? Okay, so we got magnitude and direction, but it's really easy. All I did is plug in minus q, right? And so I could just plug in minus q kind of almost, you know, without thinking into the formula, and I would get the right electric field and direction and magnitude. So I'd get the right electric field vector E minus. Okay, so then what if now the only difference is notation? And again, you're going to bump into this because some people write minus q, some people write q negative. In fact, some people do both. It just depends. You know, I don't know what they had for breakfast or whatever. And like, okay, and I'm going to write q is negative. So now you have to remember that q is a negative number, right? And so you're like, well, doesn't it work the same? Don't I just plug it in, right? Because E minus, after all, should be kq divided by x naught squared x hat, which is actually correct. So well, aren't you splitting hairs here, John? Like, why are you making a big deal out of this? Well, I'm making a big deal because this thing here, it looks positive, but is really negative because q in and of itself is a negative number, right? So that's the thing. What you don't want to do, and it's a common error, is to say, well, the default in my brain is if I see like three variables stacked like this, kq over x naught squared, my tendency is to think, well, it's just a positive quantity, because typically, especially in 8a, where mass is always positive, right? So we don't have this negative mass issue like we have negative charge. So there's a lot less negative signs floating around. And typically, if I see kq over x naught squared, I'm like, well, it's positive, right? And so I might say, oh, well, no, wait, it's positive, but I want it to point left, so I need to add a minus. Okay, now you don't want to do that, because if you do that, you're double counting minuses, right? You're saying this minus here is going to apply to x hat, which means to the left, but the fact that q in and of itself is a negative number, right? Which means that if you were going to compute a numerical value, you would plug in, let's say, I don't know, minus 10 nanocoulombs for q. Well, the two minuses are going to cancel each other out. You're going to get something positive times x hat, or carried by x hat, I should say, and that would be to the right. So you're going to screw up your direction, right? And so that's the issue that I have, right? Is that this notation here, you tend to double count negatives when you use it. And so if you ever find yourself off by a negative, that's usually why. And again, it's a bummer. It'd be nice if everybody used this or everybody used this. You could say one or the other. But the truth of the matter is you're going to find both, and you just have to be super careful when you're writing down these electric fields in problems. Now, is there a workaround? I mean, here's what I would do, or here's what I do just to make sure. So I will write E minus without an arrow at first, meaning I only want magnitude. Okay, so I want to write a positive quantity. Okay, so this is k. Q is positive, right? So kq over x naught squared, that is actually magnitude. Now, if I only want magnitude, fair enough, I'll stop there. If I want direction, I'll say, okay, well, it's really along minus x hat. I'll add it later, and then I'll add the arrow here. Right? When there's the arrow above E minus, it means it's a vector, so it's not just magnitude, it's also direction simultaneously. So you need both. Okay. Now, how would I deal with the other scenario? Well, with the other scenario, I'd do this. I'd start with magnitude, right? So I would write E minus is k absolute value of Q, right, divided by x naught squared, that's a positive value. So that's technically magnitude. And if I want direction, I would do this. So I'd say E minus as a vector is going to point along the minus x hat direction. Okay, but don't confuse the two. Don't confuse this with this. There's a difference, right? And so this is a positive value. It's a positive number. I've gotten rid of the issue that Q is a negative quantity by putting an absolute value. And then I've added direction because let's say I wanted both magnitude and direction. But if I just wanted magnitude, I would write it like this so that I don't run into any issues. So it sounds like it's not a big deal, and you know, it's not that big of a deal, I suppose, except that it causes a lot of confusion. It's hard to identify where the confusion comes from. You're like, well, sometimes I plug in minus 10 nanocoulombs, sometimes I just plug in 10. Like, how do I know what I plug in? And it's because of this difference between writing the minus sign out front versus not. Okay, and typically it only arises with positive charges. I'm sorry, with negative charges, not positive charges. I don't know what I'm saying. So obviously positive charge is not the issue. It only arises with negative charges. And that's typically where you find yourself being off by a minus. So something to keep in mind. You have to know that it's a thing. You'll find that if you pay attention to it and you know it's an issue and you're careful, usually you're fine. But if you're not cognizant that this is an issue, then it's easy to miss, and therefore it's easy to double count negatives. Okay, so that was a question that I got a lot, and it's usually a question that I do get a lot every semester, so I thought it was worth clarifying off the bat rather than getting too far down into the course and not having addressed it. So now that we've addressed it, let's quickly talk about electric flux and tie it to Gauss's law so that we can then do couple problems. We're going to do two super classic problems that in one form or the other they're going to be on the exam, very likely anyway. So if not on midterm 1, possibly on the final. Okay, so electric flux. Now electric flux is a really interesting quantity. It's a bit of a weird one, and I'm going to draw it like this, and there's, this is in more details in the lecture notes, but this is going to be an area. Like, you can think of it as, it could be a frame, it could be a sheet of paper, it doesn't matter, it's an area. And we're going to try to measure how many electric field lines go through this area. All right, so I need to draw an electric field. I'm going to draw an electric field like this. All right, this is going to be E. And now E doesn't have to be the same everywhere, but I will draw it as being the same everywhere just out of simplicity, right? So what I want to show is the E electric field E is poking through this surface, right? And perhaps there's more than one electric field line, right? You could imagine that there's maybe a whole bunch of them. You could draw as many as you like that are floating around and that are going through this surface, okay? And the question is, how many? Now, that's a bit of a tricky question because you might want to say, well, can't I draw as many field lines as I want? Like, in theory, like, how do I know how many field lines I draw? Well, and that's a really good question. It's like, well, to a degree, it's kind of up to you. But so let's assume that I draw 3 here, just, to illustrate this. But yes, there's as many field lines as you want. But we're going to try to count how many go through this surface, right? Now, a simple analogy and where this comes from mathematically is how much water is flowing through my fishing net, right? So flux is actually a quantity that makes a ton of sense in the real world. How much wind is hitting my sails, or how much, better yet, how much water flows through my fishing net, because there's the notion of flowing through. And so you can see why one might want to know that. And so then you can extend it to things that are not necessarily, that you can't necessarily grasp, like, water flowing through a fishing net is pretty straightforward, but electric field flowing through a surface, like, hey, I've never seen an electric field, but I suppose I can, it has direction, it has magnitude, so you could argue that there's a certain amount of it that goes through this surface. Okay, so electric flux is a measure of the number of, well, electric field lines. Of course, we only know about electric field lines for now, that traverse or go through a surface. Okay. And if, you know what, if it were a finite number, right, if you like had like, I don't know, 50 field lines and you were trying to count them, well, you just add them, right? 1, 2, 3, 4, 5, all the way up to 50. You're like, cool, done. Of course, that's not really how it works, because the reality is that we have, you know, a continuous distribution of field lines across this surface that has an area A. And so we have to get good at counting field lines. And so what we would want is we would want to know, well, of all this area, how much area is needed for one field line to go through. Okay. And that'd be a little piece of area there. Right. So let me draw it in a different color so it's not so hard to see. Right. So I would draw a little slice of area. Right. This is the tiniest area that we can imagine that's non-zero, or a different way to put it is that it's the area through which I can only fit one electric field line, let's call it. And we're going to give it a name. We're going to call it, in magnitude, it's going to be dA. Right. And by the way, if I wanted to find the entire area of the sheet, I would compute the integral over the area. Now, sometimes there's two notations, right? You could write two integral signs in dA. Or you could just write one integral sign, subscript a, dA, to mean that we're really integrating over area. Okay, say this is the same thing. This is the same as this. Sometimes you'll even find people that do that, and that's like super overkill, but I am guilty of that at times. Okay, so the point is, if you take all these dAs and you add them together, you get the whole area A. Like, it's kind of, if you know, when you integrate dx, you get x, really, right, which is the length of your interval, right, because if it's from A to B, you get xb minus xa, and that's how long your interval is. So it's the same idea. If you add all the dx's together, it's a continuous sum, you get x, and that's the length of the interval in question. So here you add up all the dAs, that's a continuous sum, you get the area. Now dA, we're going to do something even smarter with dA. We're going to do this. We're going to say, okay, well, dA is important. It's the amount of area through which I can fit one electric field line. But you know what? Electric field here is at an angle. If I think of its components, right, there's going to be a component that's parallel to the sheet and a component that's perpendicular to the sheet. Well, guess what? The component that's parallel to the sheet, let's call it E parallel, not really interesting, because guess what E parallel doesn't do? E parallel does not traverse the surface, right? It grazes the surface. It's within this plane, right? It doesn't poke through. Now, E perpendicular, though, does, right? E perpendicular, by definition, is going to be, well, perpendicular to the area, which means that part of the electric field, that component, is going to go through this, this surface, okay? So I'm going to create a vector. It's going to be super clever. It's vector dA. Okay. Now vector dA has two properties. One is direction. It's perpendicular to the sheet because, well, that's the direction that the electric field needs to be in to go through the sheet or through this surface. And then, but it's also going to have a magnitude equal to dA, which is the little amount of area through which I can fit one field line. So if I think about it, the tiny amount of flux, I'm going to call the flux phi sub E, that's the electric flux. The tiny amount of flux from one field line is going to be E perpendicular times dA. But E perpendicular, so long as I take care to define the angle theta here with respect to dA, is going to be E cosine of theta dA. Okay, so that's the perpendicular component times the area. And flux, if we're counting the number of field lines that go through an area, kind of makes sense intuitively that the stronger the electric field, the more flux, the greater the area, the more flux. And so this, you can write E cosine theta dA, there's nothing wrong with that. You will see it written E dot dA. It's a very, very clever notation to have dA as a vector, because remember, A dot B is magnitude of A, magnitude of B, cosine theta. Okay? So that is the amount of flux from one field line. If I want the flux over the entire area, I will say that the flux is going to be the integral over the entire area of E dot dA. In other words, E cosine dA, cosine theta dA, sorry, integrated over the area. That's going to be the flux for the whole surface here. Okay. Now, do I care about electric flux? Actually, not exactly. I need to know what it is, and in the context of Gauss's law, I have electric flux is equal to Q enclosed over epsilon naught. But really, not that interested in it. Right? And we'll see why. Because the goal of Gauss's law is not to compute electric flux, it's to find the electric field. And I can do that under very specific conditions that require that whatever charge I'm looking at have a lot of symmetry. Okay, so then that's just flux. Okay, so this is the definition of flux. Okay, and Gauss's law is going to tell us that the electric flux is going to be equal to Q enclosed over epsilon naught, where Q enclosed is the amount of charge enclosed in the surface. Okay, so the surface through which I'm going to compute flux, well, the surface must be closed. Okay, so it has no edge and no holes, right? So a soap bubble is a closed surface, right? A cylinder, a toilet paper roll is not a closed surface, right? Because this is a hole, this is a hole. Now, if you come along and you put a piece of cardboard here and a piece of cardboard here, and you close up the toilet paper roll with end caps, right? Then it is a closed surface. It has no holes, it has no boundary, right? So if you're an ant and you're walking on it, you can't fall into it, right? Same thing with the soap bubble. If you're an ant and you're walking on it, you can't fall into it. There's no hole in the soap bubble for you to fall into, right? So Gauss's law applies in the context of a closed surface. And so this could be rewritten. We know that electric flux is going to be the double integral of E dot dA. I'm going to say that it's Q enclosed over epsilon naught. Now the problem is that notation does not capture the fact that the surface has to be closed. And so what we do is we add a ring around the integral to signify that the area, or the surface rather, over which we're computing the flux is a closed surface. So the ring means that the surface is closed. Okay, so something to keep in mind. And again, is it true that for any closed surface, the flux through that surface of the electric field is equal to Q enclosed over epsilon naught? Yes. Is that practically useful? No. Because I never care what this is. I know it's always equal to this, and it's really easy most of the time to find Q enclosed, but I don't care what the flux is, okay? The art of Gauss's law, the goal, is to choose a surface, which we're going to call a Gaussian surface. Choose a Gaussian surface on which E and cosine theta. I should say over which, if we're actually trying to speak English here. A surface over which E and cosine theta are constant. Because if E and cosine theta are constant, then this happens, right? Then the flux over the closed surface of E dot dA is going to be equal to the flux over the closed surface of E cosine of theta dA. But integrals don't care about constants. So E cosine theta can go live outside. Okay, and I wind up with then the double integral over the closed surface of just dA. Well, guess what that is? That's equal to A. We said that before. So I get EA cosine theta. And my goal is to get my hands on this. Okay, so we want this. That is what we're solving for. So if I then set flux, which is this, equal to Q enclosed over epsilon naught, I can solve for E because I've managed to extract E out of my integral. But if I have just this equal to Q enclosed over epsilon naught, there's no saying that every single time I can do this and I can pull E out of the integral. In fact, most of the times I can't, right? Because I need E and cosine theta to be constant over the surface. And if they're not, then they don't get to do this. They don't get to go live out front, right? They have to stay in the integral, and then well, that's it. Like, I'd have to compute this, and cool, it would give me flux, but guess what? I don't care because I want E, which means I have to have E times area times cosine theta. Then I'll set it to Q enclosed over epsilon naught, and I'll get E. I'll solve for E. All right, so that's Gauss's law is a little weird like that, and there's a saying that's to, apply Gauss's law, you have to believe in Gauss's law in a way, because it is a little curious how it applies, and it involves a quantity which is flux, which we actually don't care about. We only care that flux breaks down into this product here, so that we can get our hands on the electric field, and this typically only happens when you have enough symmetry. All right, so the symmetries that work are infinite wires and cylinders. They're said to have cylindrical symmetry. We're going to do one of those. Infinite translational symmetry, which is basically an infinite sheet and an infinite slab. That's covered in the lecture notes. And then spherical symmetry. So point charges or spheres of charge or spherical shells. And we'll do one of those because along with the infinite cylinder with the cylindrical symmetry, we will see what the two main categories of problems are, right? The two geometries that really work and that you find the most often associated with Gauss's law. Okay, but Gauss's law is a great tool. Once you get it, you're going to love it. It's going to be the fastest way to get the electric field when it applies. But at first, it's going to seem super weird. Not just this part here, but also the fact that we only care about the charge that is enclosed. And even if there's charge outside, it doesn't matter. It doesn't contribute to what we're trying to solve for. So let's not spend too much time on abstract theory, and let's just dive into the meat of this. And let's learn how we would apply Gauss's law to these two superclassic symmetries. Okay, cylindrical symmetry in this case, and then we'll do spherical symmetry after. And these problems are problems where if you've never done them before, I wouldn't even wake up in the morning to go to the first midterm. I just stay home. Like, there's no point. There's no way you don't get something like this in some form or another. It's so unlikely that you have to be really comfortable with both of these problems. So we have an infinitely long cylinder of radius r that is shown below. And assuming we have a conductor which has charge density sigma on its surface, find the electric field as a function of r. Basically, find the electric field everywhere. Okay, so before we dive into solving for the electric field in question 1, let's do the following. let's acknowledge that there are two regions of space. There's region 1 here and region 2. I use Roman numerals. You don't have to, but just it's habit, so you'll see me do that. But the point is, these two regions are different. There's no reason why inside the cylinder I should have the same electric field as outside. Now maybe I do, could happen, maybe, and then I'll figure that out. I'll just, find E in this region, find E in this region, and then I'll say, oh, guess what? They're equal. What a coincidence, right? But it would be a coincidence, because most of the time, the electric field in each region is different, okay? Now this is hollow, just so we're clear, right? It is a shell, so there's no, if you can look straight through it, there's just air inside, and the charge is distributed over the surface, right? And because it's infinite, right, it extends infinitely up and down like this, the electric field is going to have a very specific shape, which you probably already know, which is that it's going to be radially outward, just like the infinite wire of charge. Right? The electric field is going to radiate outward in the horizontal plane. And the reason for that, now this is perspective, by the way, just so we're clear, right? These field lines, they all align with this point here, right? They all, right? And you got the same thing out here, right? They're going to leave like that. So they're all in the horizontal plane. And the point is the electric field will be everywhere perpendicular to the cylindrical wall because it has the same amount of charge above and the same amount of charge below if this is an infinite cylinder. So there's no reason why the electric field should prefer this direction over this one, right, relative to the surface. What it can do is just, if the surface is positive, it will depart the surface perpendicularly to the surface. So in theory, not in theory though, but typically, that's a guarantee. In lecture, and if it hasn't been the case, you should ask for a refund, but in lecture you should have done the infinite wire of charge, which has the same symmetry and therefore the electric field is radially outward. Okay, but it's important to keep it in mind because this is going to dictate what we choose for a Gaussian surface. Now, spoiler alert, all you need to get through 8b is either a cylinder or a sphere for your Gaussian surface. Now, it has to be closed, so it has to be a cylinder with a top and a bottom with end caps. But a closed cylinder or a sphere will get the job done every time. It's just a matter of you have to choose the right one given the problem. And the way you choose is based on what the electric field looks like. Okay, so the electric field has no preferred direction in the horizontal plane, right? It just leaves the cylinder equally in all directions in the horizontal plane. And then the vertical direction is different, right? The vertical direction doesn't matter. You'll see the same thing everywhere, right? And so between a sphere and a cylinder, which one matches more the geometry of the electric field? Well, the cylinder, right? The cylinder, you'll see the same thing along the length. And if you go around, there is no difference. You can't really tell as you go around the cylinder where you are, right? You always see the same thing. And so what we're going to do in region 1, and we have to start, I typically start from the inside and work my way out. You don't have to, but I think it's pretty common, right? So we're going to start with region 1. And region 1 is going to be the region inside here. And I'll just draw a few field lines just so that we can see what's going on, right? This is the electric field. And again, it's radially outward, right? Well, that's misleading now, isn't it? Let's just leave it like that. It's fine. So this is the electric field. We'll call it E sub 1 for region 1. And I'm going to draw a Gaussian cylinder that is going to be centered on this cylindrical shell. And it's going to have a radius little r that is less than big R. Right? So if I want to find the electric field in region 1, I need to choose a Gaussian cylinder that is going to have a radius little r that is smaller than big R. In other words, my Gaussian surface has to live within the region where I'm trying to find the electric field. Okay? So then let's see if it'll let me do this. Yes, okay, perfect. All right, and then this just for clarity. Boom, 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 there we go. And so now what I have to do is I have to and I'm sure you've seen this before, but let's just go through it. I have to show that I have three different surfaces, top, bottom, and cylinder wall, and so I need three different normals, right? So I have dA1, I have, we'll call this dA3, perpendicular to the top and outward, perpendicular to the bottom and outward, and then I'm going to have dA2, perpendicular to the cylinder wall and outward. Okay, so we always choose the outward normal if we have a closed surface. That's a convention from math. You don't get to argue with that. And then dA1, dA2, and dA3 are perpendicular to the different surfaces, right? And so overall, if I want to compute my flux through my closed cylinder, I would be computing the integral of E dot dA, and I'd put a ring around this integral because overall my cylinder is closed. However, my cylinder is made up of three different surfaces, and so I'm going to actually have to break it up into three portions. So I'm going to have to do the flux through the top. That's going to be E dot dA1. I'm just going to add A1 here. I know it's overkill, but just to keep track. This is going to be flux through the cylinder wall. That's going to be over the area A2, the E dot dA2. I suppose I should call it E1 just to be consistent. This is E in region 1, plus the same thing through the bottom, so through area A3, E1 dot dA3. Okay, now, just to be clear, and this is almost detail, but forgive me, I have to be anal on this stuff. Here we have a ring because the whole cylinder is closed. Here there is no ring because individually A1, A2, and A3 are not closed surfaces. A1 is just this, A3 is just this, and A2 is the cylinder wall, but none of these surfaces are closed. So none of these integrals here get rings. It's just that when you put everything together, yes, you get a closed cylinder. Okay, so I'm being super picky, but just to be clear, that's why there's no ring on those integrals. Okay, so now we can do the following. We know what E dot dA is, right? And by the way, let me just draw, just for reference, let me draw one field line up here. What I want to keep in mind is that it's perpendicular to dA1, and the same thing is true about dA3. Right. So if I apply the definition of the dot product, I'm going to have the flux through area A1 of E1 in magnitude, cosine of the angle between E1 and dA1, which is 90 dA1, plus for the cylinder wall, which has area A2, I'm going to get E1 cosine of the angle between E1 and dA2. Okay, well, look, wherever I drew dA2 here, here's a field line E1, and they both point in the same direction, so the angle between those two vectors is 0, then dA2. And then plus, I'm going to have to put it here just to fit it in, integral over A3, E1, cosine of the angle between E1 and dA3, which is 90 dA3. Okay, now what do we get? Well, we get the following. We get that this first integral here, the flux through the top of the cylinder, is going to be 0, right? Because cosine of 90 is 0, so this all goes away, meaning there is no flux through the top. Well, of course not, because E is going to be in the horizontal plane, meaning it never pokes through the top of the cylinder, right? It never pokes out or pokes in. It's just parallel to that surface, so there's no flux from E1 through that surface. With the same logic, there is no flux from E1 through the bottom surface either. There's only flux through the lateral cylinder wall, right? This is non-zero. Okay, now by the way, on my cylinder here, on the wall of the cylinder, E1 is the same everywhere. It should be, right? Everywhere on the cylinder wall, I am a distance r from the center of the cylinder. So there's no reason why E1 should be stronger here than here or here, right? As I go around the cylinder, I'm everywhere the same distance from the center. The electric field is going to be constant in magnitude and in direction on the surface area A2, on the surface A2. And so E1 comes out, cosine of 0 is 1 anyway, and I have to find the integral over A2 of dA2. Turns out that's not so bad because it's pretty easy to find the surface area of a cylinder. Now if you've forgotten how to find the surface area of a cylinder, let me just do it here real quick because there's no way you get through the class without needing this, so let's just address it now. This is a cylinder, yeah? Well, not yet, but it is going to be one. This is going to be a cylinder. I'm going to give it a radius r and a height or length, call it L, which I should have, that's my bad, I apologize. I should have drawn L here. Should have specified the length of this thing. Okay, well, if I take a pair of scissors and I cut my cylinder, so let me do this for clarity, okay, and I cut my my cylinder along this vertical line. So along the length, I take a pair of scissors and I cut it up, and then I fold it out on the kitchen table, right? I'm going to get a rectangle, right? Now my rectangle is going to have two dimensions. First of all, it's going to have one side length L, that's pretty obvious, but then this has to wrap into a circle of radius r, and so it has to have a length equal to the circumference of that circle, which is 2 pi r. And so the area of this thing is just, well, it's a rectangle, so guess what? Multiply the side lengths, you get the area, you get 2 pi rl. Okay, so flux through the cylinder wall is going to be E1 times 2 pi rl. Okay, which is good. It's what I wanted, right? I wanted to get flux, but so that it breaks down into E times area. Okay, that's one half of Gauss's law, right? The other half is evaluating Q enclosed over epsilon naught. And then I'm going to argue that both of these are equal to each other. It's going to give me E1. So Q enclosed, well, Q enclosed is the amount of charge that is enclosed by my Gaussian cylinder. So it's the amount of charge that lives in here. Okay. Now you might say, well, hold on, isn't there charge out here on the cylinder wall? And yes, there is, but it's not enclosed, so it doesn't matter. That's the tricky part about Gauss's law. The charge that's not enclosed is irrelevant. Second thing is that, yes, there is. In fact, there is only charge on the cylinder wall, so that within my Gaussian cylinder here, there is no charge whatsoever. And with no charge whatsoever, when I equate these two quantities, I'm going to get E1 is equal to 0. Right? So I'm going to say that by Gauss's law, E1 2 pi rl is equal to Q enclosed over epsilon naught, which is 0. And so E1 is equal to 0. There's no electric field inside this hollow cylinder. Now careful, it is a hollow cylinder. We're going to do the solid cylinder after, right? But this is a hollow cylinder, so there's no charge, okay? So that's the electric field in region 1. That is not all. We have to then do region 2 because we wanted to find the electric field everywhere. So we have to repeat this process and find the electric field in region 2. So let's come down here. Let me make another copy of this just to have for later. Okay. And then let's focus on region 2. Right? Region 2 is going to be outside of this cylinder of charge. And that's for little r greater than big R. Okay. Now, the same logic, yeah? We're going to draw a Gaussian cylinder. That's because of the shape of the electric field, right? And we are going to make it big enough that it lives in region 2. Okay. And we're going to compute the flux through it. We're going to equate it to Q enclosed over epsilon naught. And we're going to see what the electric field in region 2 is equal to. Okay. Now, I'm going to draw E2 like this, just to show it, right? It leaves the cylinder perpendicular to the cylinder wall. This is going to be dA2, like it's the outward normal for the cylinder wall. And I still have dA1, and I still have dA3. And this is a cylinder that has a radius, little r, and a length or a height L. So same thing, just a bigger cylinder, so that it now lives in region 2 because I want to find the electric field in region 2. Now here's where we can recycle some of the work we've done. It turns out, if you look at this, there is going to be no difference between finding flux in region 1 and region 2. Right? So humor me here. If I take this thing, like all of this, and I copy, paste it right here, the only thing I'm going to have to change, right, is going to be E1 into E2. So the only difference is that I need to write E2 instead of E1. So let me get rid of E1. Oop, I missed a piece now, didn't I? I should have down here, should have grabbed that, my bad. This is going to be 0. Okay, so now we have the same thing as above. So the only difference is that the electric field I'm going to find is the electric field in region 2. But flux does not care which region it's being computed in. Flux only cares, so it doesn't know if you're in region 1 or in region 2. All it knows is that it's being computed through a cylinder, and that the shape of the electric field means that there's only flux through the cylinder wall. That's it. So that's all it cares about. So flux doesn't change. However, the amount of charge that we enclose now will change, because before our cylinder was too small to enclose any of the charge sigma, charge per area, that lived on the outer, or that lived on the wall of the cylinder, right? So we didn't include any of it because we're like, well, we didn't grab any of it. But now my Gaussian cylinder is big enough that it encompasses this cylinder of charge, meaning that it is going to encompass a certain amount of charge that lives on the cylinder wall. Okay, now we have to be pretty careful here, is that sigma, which is charge per area, has to be multiplied by the appropriate area. And the appropriate area is just the area of the cylinder wall, but of the actual solid cylinder, not the Gaussian cylinder. In other words, there is no charge here between my Gaussian cylinder in red and my solid cylinder, right? Sigma only lives on the gray cylinder of charge. So I have to multiply sigma by the area that is going to be 2 pi, careful, big R, L, and then divide that by epsilon naught. But that would be the area of the gray cylinder of charge. Makes sense. If I multiply sigma by that, I get the charge stored on the gray cylinder of charge. I do not want to multiply by 2 pi little RL. That would be a surface area here on which there's no charge. It doesn't make any sense to do that. So you have to be very careful about that. Okay? And then you can say, all right, well, by Gauss's law, these two quantities are equal to each other. Right? So let's do that. Let's say that by Gauss's law, these two quantities, the flux through the Gaussian cylinder and the charge enclosed divided by epsilon naught, where the charge enclosed is going to be the charge that lives on the gray cylinder, are equal. So actually, I don't know why I did that. It's kind of silly. Let's just do this, right? And what we're going to find is that, okay, 2 pi goes away, L actually goes away. Now that makes sense because if I truly have an infinite cylinder, it shouldn't matter how long I make my Gaussian cylinder. I should see the same thing everywhere, right? And so E2 in magnitude is going to be sigma r divided by epsilon naught little r. That's going to be E2 in magnitude. So my answer is going to have to be something like this. Now I have two options. I can write sigma r divided by epsilon naught r. And then I would say, well, this is for little r greater than or equal to big R. And then I have to include direction. Right? I have to say, well, this is radially outward. So that's one option. And if you don't like vectors, it's a good option. Or you can say, well, it's vector E2, which has magnitude this, which is positive, and then along r hat. Okay, now r hat's a little confusing because in the case of a cylinder, r hat is just radially outward, but only in the horizontal plane, right? So it points radially outward, but doesn't point. It's not like if you have a sphere, then it's different, right? R hat is radially outward, but in and out of the page as well and all that. So that's just a different case when you have a point charge. R hat, when you have cylindrical symmetry, just means radially outward horizontally, right? Perpendicular to the axis of the cylinder. But that would be E2. Okay. Now in and of itself, that's a pretty good problem, and the problem could stop there, and that'd be okay. It's just I would feel like I'm cheating you a little bit, so I actually added a question to this problem at first. First it was just this, but then I added a question so that we could talk about, well, what happens if now this is an insulator, right? An insulator, which means that it can carry charge distributed throughout its volume, right? Instead of just having charge carried by the cylindrical shell, right? So now this thing is no longer has sigma, it has rho, charge per volume. It has charge distributed throughout it, everywhere, and the charge is stuck in place like fruits in a fruitcake because it's an insulator. What changes, right? Well, now we can go probably a little bit faster here, right? Not much is going to change as far as flux because I have the same geometry and I have the same approach, which is region 1 first, then region 2, Gaussian cylinder inside region 1, Gaussian cylinder inside region 2, find the flux, let's go, right? So I would do, in fact, I don't want to skip the illustration here, but I also don't want to redraw the whole thing. So let me do this. I could take this, let's take this whole thing, right? Just duplicate this guy and bring it down here. Okay, now by the way, let's duplicate this guy while we're at it, and we'll bring it down here for later. Okay, so we'll come back to that. Okay, but there's no difference. The only difference really is rho, right? Now I have charge per volume rho instead of sigma. But I would draw the same thing. I would draw a cylinder in region 1. I would draw dA1, dA2, dA3. So this start with region 1. So R is going to be less than big R. I have a cylinder, I have the electric field, everything's the same. And if I compute flux, the electric flux is going to be the same, right? It doesn't know what region it's in. It doesn't know if you have a solid cylinder of charge or a hollow cylinder of charge. It couldn't care less. It cares about the geometry of the electric field, which is radially outward. That's all it cares. Okay, so what will change? Well, what will change is Q enclosed over epsilon naught, because before, when my Gaussian cylinder was inside my cylindrical shell, there was nothing contained in my Gaussian cylinder, it was just air. But now that's not true, right? I have charge distributed throughout the volume, so I have to take rho, charge per volume, and multiply by the volume that carries charge, which in this case is the volume of the Gaussian cylinder. So it's area of base pi r squared times height L, and this is divided by epsilon naught. And then by Gauss's law, I'm going to have E1 2 pi little rl is equal to rho pi r squared L over epsilon naught. 2 pi goes away, r cancels the square, L goes away. No, 2 pi doesn't go away, just pi, my bad. Pi, whoop, there we go. And we get E1 is equal to rho r over 2 epsilon naught. And you would just write radially outward if you want, or you could use vector notation if you prefer. It's much more common to use vector notation. So if you're looking at an answer key, you'll probably see this, but there's nothing wrong with writing in English radially outward. Everybody will understand what you mean. Okay, so that's E1. So E1 is no longer 0. In fact, E1 is proportional to little r, meaning the further I get from the axis here, and the closer I get to the edge where little r is equal to big R, the stronger the electric field becomes. That makes sense because I enclose more and more charge. So now let's do region 2, right? Region 2, the setup would be this, same as before. The difference is I would no longer have sigma, I would have rho, right? And I would write that in region 2, which is going to be for r greater than or equal to big R, the electric flux, again, has no clue that it's being computed in region 1 or 2, or if it's a hollow cylinder or a solid cylinder. It's going to be E2 2 pi RL, okay? And Q enclosed over epsilon naught, it's going to be very similar to what we just did. We just have to be super careful. We're going to take rho and multiply by volume, but this time, careful, the volume is the volume of the solid cylinder, because charge only lives on the solid cylinder. There is no charge in the gap here between my solid cylinder and my Gaussian cylinder. It's just air. So it's going to be rho multiplied by, this time careful, pi big R squared L divided by epsilon naught. And by Gauss's law, these two quantities are equal to each other. Okay, so we get E2 times 2 pi RL is equal to rho pi R squared L over epsilon naught. Pi and L cancel. Makes sense that L would go away because if it's truly an infinite cylinder, then L shouldn't matter. And then we're going to get E2 in magnitude is going to be rho R squared divided by 2 epsilon naught little r. Okay, and again, you could write radially outward in English, or you could just use the vector notation. E2 as a vector is going to be this times r hat. Okay, and now note that little r is now in the denominator, and that makes sense because if I increase little r, in other words, if I increase the size of my Gaussian cylinder, I do not increase how much charge I enclosed. I already enclose all the charge here. So as I get further, now the electric field is going to decrease in magnitude because making my Gaussian cylinder bigger only carries me further out from the cylinder of charge, and I've already enclosed all the charge that I can enclose. So E just decreases as 1 over R. Okay, so really good problem, and really important, to understand the distinction between the hollow cylinder of charge and the solid cylinder of charge. But both are extremely common. Again, I would never show up for midterm 1 without knowing how to solve both of these. And when I say solve them, I don't mean spend 15 minutes and, thinking through it and pondering. I mean solving it in 3 minutes flat, because there's not much to it. You should know this kind of off the top of your head almost. And typically it's not what the problem is trying to ask you to do, right? This is a good practice problem to kind of get warmed up with Gauss's law and understand how to apply it. But on an exam, it'll be question 1, and then there's 3 more questions that require that you find the electric field first, and then it becomes interesting. That's when the problem really starts. So just something to keep in mind. Okay. Let's move on to this problem here, and we're going to go through it. It is uncanny how classic this problem is in one form or another. So we're going to have to learn how to solve this, and it's a very specific method that everybody's going to tell you, oh, well, it's obvious. It's common sense. And there's nothing common sense about it until you've done it. In fact, probably you have to do it 2-3 times before it becomes common sense. But that you would sit down and just think of it on your own is pretty much absurd. So we have the following. We have an insulating sphere that carries a net charge Q that is placed at the center of a spherical metallic shell which has inner radius B and outer radius C. So the shell has a thickness, and Q net is 0 on this shell. Now, of course, it's a conducting shell because it's a metallic shell, right? And yeah, okay, Q net is 0, but that doesn't mean that there's no charge at all. It just means I have as much positive charge as I have negative charge. So I have to keep that in mind, because in a conductor, charge is free to move and rearrange, and it will. Now, it won't if there's nothing here in the center, right? It just stay as is, it's happy as it is. But if I put a positive charge, or a positive sphere of charge, in the center, the negative charges on the shell are going to be pulled inward, and they're going to come live on the inner surface. So I'm going to get charge separation within the shell, and I'm going to get an amount of charge Q inner. And then the positive charges on the shell are going to try to move as far away as they can from this positive core, so they move to the outer surface, which means I'm also going to get Q outer. Now, by the way, by conservation of charge, which is an important concept we'll come back to later when solving, by conservation of charge, Q net, the net charge on the shell, whether it's 0 or not, is going to be, by definition, Q inner plus Q outer, right? That's where they come from, these two quantities. Like the Q inner and Q outer, just they separated, but overall they added up to Q net initially, right? So that's a really important concept to keep in mind. And it's important to realize that there is charge separation that occurs. Now, this is why the first question says, what is the surface charge density on the inner surface? And then question 2, same question, on the outer surface. Okay, well, okay, the truth is then like sigma inner is going to be the charge on the inner surface. We called that Q inner. We need to solve for it, but there's going to be a certain amount of charge, divided by the surface area of the inner surface, which is a sphere of radius B, and so it has an area of 4 pi b squared. And then sigma outer is going to be the amount of charge stored on the outer shell, or the outer surface of the shell, that's Q outer, divided by the surface area of this outer surface, which is 4 pi c squared, because it is a sphere of radius c. So that's what we're looking for, but really what it means is that we have to be able to get Q inner and Q outer. Okay, and fair enough. If I need to get Q inner and Q outer, I need to kind of think this through and figure out how I'm going to do that, because it's not obvious off the top of my head how I would. Now, the good news is it's a classic question and it always solves the same way. Bad news is there's no excuse, like you have to know how to do this. Like, and then, you know, GSIs will tell you, oh, it's common sense. And like, yeah, no, okay, well, not common sense enough that I'll come up with it on my own. But if you show me a couple times, then, and I know that it's actually a thing, then yes, okay, I agree, it's common sense. So here's how we find Q inner and Q outer. Well, we do have conservation of charge. So it suggests that because we know Q net, which doesn't have to be 0, even though here it is, maybe if I know Q inner, then I find Q outer using conservation of charge, which is what we're actually going to do. But then how do I find Q inner? Okay, so here we have plus Q. We have Q inner that lives on the inner surface of the shell, and Q outer that lives on the outer surface of the shell. Okay, you with me? All right, so here we go. Okay, now in addition to that, I know that everywhere inside this conducting shell, the electric field is 0, because the shell is a conductor. And in conducting material in electrostatic equilibrium, the electric field is zero. So this is a method that I call, quote unquote, Gauss's law in reverse. It is not an official name, it is what I choose to call it. And I say that it's Gauss's law in reverse because typically Gauss's law is used to find the electric field. And so you would find flux, find Q enclosed over epsilon naught, solve for E, just like we did in the previous problem. But the truth of the matter is here we're going to go backwards. We're going to say, well, we know the electric field. Let's conclude something about Q enclosed. So, if I choose a Gaussian sphere that is just big enough that it lives in the conducting shell, then I can say that the flux through my conducting sphere is going to be zero. That's because E is equal to zero. Okay, because E is equal to zero in the shell. So if there's no electric field in the shell, there's no electric field lines to go through this Gaussian sphere, either in or out. There's just no field lines, so there's no flux, full stop. No flux through the sphere. So therefore, by Gauss's law, we must have Q enclosed over epsilon naught is equal to zero in this Gaussian sphere, which of course just means that Q enclosed is zero because epsilon naught's a constant and dividing by a constant is never going to give you zero. So really we're saying that Q enclosed is zero. All right, well, what is Q enclosed? Well, Q enclosed is plus Q, that's the charge on this thing, plus however much charge I enclose in my Gaussian sphere. And remember that to apply Gauss's law, you have to believe in Gauss's law, meaning that the only charge that matters is the enclosed charge. Is there Q outer on the outer surface of the shell? Yes. Does it matter? No. Is that weird? Probably, but I'm just going to follow the rule. It's not enclosed, so it doesn't matter. But guess who's enclosed? Q inner is enclosed. My Gaussian sphere is just big enough that it grabbed Q inner on the inner surface. And so I get Q inner is equal to zero. I'm sorry, Q plus Q inner is equal to zero, which of course means that Q inner is minus Q. Okay, so the amount of charge that gets pulled onto the inner surface of the shell is exactly opposite the charge in the center. In other words, plus Q in the center just has enough strength to pull onto the inner surface of the shell. An opposite amount of charge, exactly. No less, but also no more. Right. So then we know Q inner. Okay, well, actually, if I know Q inner, then my answer to question 1 is that sigma inner is Q inner over 4 pi b squared, and that's going to be minus Q divided by 4 pi b squared. So I've now answered the first question. And I'm going to answer the second question by finding Q outer, and then I'll compute sigma outer. Now what is Q outer? That's a great question. Q outer is, well, right now I don't know, but it's not something that I can get with Gauss's law, because if I wanted to grab Q outer, I'd have to make my Gaussian sphere bigger. Then I would grab Q outer, but then I would no longer have E is equal to zero, because I wouldn't be in the conducting material. So this method only works for Q inner. But that's okay, because Q outer, by conservation of charge, is Q net on the shell minus Q inner. Okay, now the shell happens to have no net charge. It doesn't have to, but in this problem it does. Minus Q is equal to Q. Okay, so we found Q outer. Let's charge Q. And therefore, sigma outer, which is Q outer over 4 pi c squared, is equal to Q divided by 4 pi c squared. There we go. We get sigma outer. All right. Okay, super classic question. Like, you have to know that this happens in the shell. You get charge separation, that there's going to be Q inner, Q outer. Q net of the shell is whatever it is. Just if it's 0, it's a little easier, but it doesn't have to be. And then you find Q inner first, and then conservation of charge gives you Q outer. Okay, and sometimes that's all we want. Sometimes in this case particularly, we wanted not Q inner, but Q inner over 4 pi b squared, and not Q outer, but Q outer over 4 pi c squared. Doesn't change anything. The net of it is that you have to find Q inner and Q outer. All right. And then we have to find the electric field, a distance r from the center of the shell. So in other words, the electric field everywhere. Okay. So I'll make a few copies of this because I'm going to need them later. All right. But before we get started, if our goal is to find the electric field everywhere, first of all, we have the right symmetry to apply Gauss's law, because spherical symmetry. Second, my charge Q is distributed uniformly throughout the inner sphere here. So I got to set up a few things before we find the electric field in region 1. Okay, now the first thing to set up is to agree that there's region 1, region 2, region 3, and region 4. And we're going to apply Gauss's law in each region, except region 3 because we already know that E3 is 0, but in regions 1, 2, and 4, we're going to apply Gauss's law, and we're going to find the amount of charge enclosed over epsilon naught, equate it to flux, and find E. Okay. But since Q is distributed uniformly over the inner sphere, I have to define rho, which is charge per volume, so that's going to be 4/3 pi cubed here is the volume of that shell. I divide Q by that volume to get charge per volume, and I wind up with 3Q over 4 pi a cubed. Okay, that's charge per area on this guy here. Okay, now why does that matter? Well, it matters because I'm going to need it to compute Q enclosed. Okay, now allow me, I'm just going to tweak this drawing to make it easier to see, but we're going to do region 1 first. So allow me just to make region 1 a little bigger so that we see what's going on. Okay, so I'm going to get rid of this. Just going to make this guy a little bigger. Okay, just so that we see what's going on. Oh, come on. There we go. Okay, so this is still an insulating sphere. It has charge per volume rho. That's all the same. It didn't change. Right? And then I know that the electric field created by a positive charge Q is going to radiate out in all directions, right? And that's by symmetry, okay, including in and out of the page for that matter. That is because I have spherical symmetry. So it's going to be E1, right? And I could draw more of these, but I don't really need that many more. So I'm going to draw a Gaussian sphere, right? Because remember, my Gaussian surface is going to be a surface, a closed, 1, 2, 3. My Gaussian sphere is going, wow, 1, 2, 3 again. It's the Gaussian surface I'm going to choose in 8b is either going to be a closed cylinder or a sphere. And I choose one or the other based on the symmetry and the geometry of the electric field. Well, if the electric field radiates out in all directions of space, meaning it has no preferred direction, then I'm going to choose a Gaussian sphere because a sphere has no preferred direction. So I'm going to give this sphere a radius r. The normal here is going to be dA. It's going to be outward because I have a closed surface. And the flux is going to be the flux through the Gaussian sphere, E dot dA. That is going to be E cosine of 0, because the angle between, I should call it E1, E1 cosine of 0, because the angle between E1 and dA is 0. And that's going to come out equal to, now, E1 is constant on the surface of the sphere, and cosine of 0 is 1. How do I know that E1 is constant on the surface of the sphere? Well, all points on the surface of this sphere are the same distance from the center. Okay, so by symmetry, it would make no sense to argue that E1 is stronger here than here and weaker here than here, or anything like that, all points on the surface of the Gaussian sphere are going to be the same distance from the center. So by symmetry, E1 is constant on the surface of the sphere. So I get E1, cosine of 0 is 1. If I integrate dA over the sphere, I get the surface area of my Gaussian sphere, which is 4 pi r squared. Okay, which hopefully that's been also covered in lecture at least once for these types of symmetries. Okay, so that's the flux. All right, and then I just need to write Q enclosed over epsilon naught. Okay, Q enclosed is going to be a little weird here. How much charge do I grab inside my Gaussian sphere? Well, a fraction of the total charge Q. And how do I find it? I take rho, charge per volume, and I multiply by the volume, but of my Gaussian sphere. So 4/3 pi little r cubed divided by epsilon naught. I should plug in what rho is, and if I do, I get rho r cubed over a cubed divided by epsilon naught. And so, by Gauss's law, I get E1 4 pi r squared is equal to rho r cubed over 3, no, not yet, no 3 there, rho r cubed, that's where the 3 is, divided by a cubed epsilon naught. How does that simplify? R squared kills r cubed, and I find that E1 is equal to rho r divided by 4 pi epsilon naught a cubed. Okay, that's what I get for the electric field in region 1. And so, oh, I apologize. No. My bad. It's no longer rho, it's Q. I knew something was off. Sorry. Wow. I replaced rho with this, basically. Okay, so what do I get? The 4/3 pi goes away, but I get Q, r cubed over a cubed. Okay, so this is going to be Q. That makes a ton more sense. Okay, Q r cubed over a cubed epsilon naught. This is Q r over 4 pi epsilon naught a cubed. Yes, that's okay. Way better. And then this is going to be E1 in magnitude. If I want to include direction, I'm going to say that it's radially outward. So E1 vector carried by r hat. R hat means radially outward, but I have a sphere, so that really is radially outward in all directions of space. You know, kind of like the light reflecting off of a disco ball. Same thing. Okay, so now I can repeat this in regions 2 and 3 and 4 to get the electric field. Right, so this is, by the way, this is for r less than or equal to a. And I should probably add that to, should box that. All right, add that to my answer. Okay. Let's now move on to region 2. Okay, so we have an electric field that's radially outward, something like this. Call it E2. Now I know somewhere a GSI is not happy with what I just drew. I shouldn't draw field lines through this conductor because there's no electric field. But I don't care. It's the electric field in region 2. I'm not worried about region 3 right now. Okay, so let's not split hairs here. I'm going to do the same thing, yeah? Choose a Gaussian sphere because of the symmetry of my electric field. I'm going to have radius r, and guess what? The flux doesn't care in which region you are. It just cares that you're computing it through a sphere, and so you're going to get the same thing. You're going to get E2 instead of E1, but times 4 pi r squared. That won't change. Okay, now what does change is Q enclosed over epsilon naught. Now, how much charge do I enclose? In fact, this is easy. If I think of how much charge lives within my Gaussian sphere, and again, I don't care if there's charge outside, it doesn't matter, then that amount of charge is just Q, because I've grabbed the entire insulating sphere. And so by Gauss's law, I have E2 4 pi r squared is equal to Q over epsilon naught. And so I should actually not be surprised with what I get. I get Q over 4 pi epsilon naught little r squared. And this is going to be for r between A and B. And it's the same thing as a point charge. Like, well, but yeah, I mean, you know, once I'm outside of the insulating sphere, I'll just add r hat for direction. Once I'm here, this thing looks like a point charge. Like, is it a point charge? No, obviously not. It has a certain size. But it's spherical, carries a charge q, and so therefore the electric field that it creates ought not be any different than the electric field that a point charge would have created. So I get the same expression for the electric field, right? The only difference, of course, is that this is only valid in region 2. It's not valid inside the insulating sphere. Okay, inside the insulating sphere, this is E1. Now, by the way, this is a common question that I always get. Once you have E1 and E2, let's say, what do you do with them? Nothing. You don't add them. They just exist in each region. So if you're focusing on region 1 after, for whatever reason, you would use E1. If you were focusing on the gap between the two in region 2, well, you would use E2, right? You don't just add them. There's just, you're finding E in each region, and that expression is only valid within that region. Okay, so that's region 2. Okay, so then region 3 is easy. We actually already solved it. E3 is 0 because the shell is a conductor. So that takes care of that. Okay, now we should do this. Right, that is for R between B and C. That's region 3. And then region 4 is going to be outside of all of this. Okay, well, not that hard. We know how to do this. The electric field, once I'm outside, is going to look like this, or at least that is my best guess, because overall I have a total positive charge. So if there is an electric field outside, which turns out there is, I would anticipate that it will be radially outward. But even if I don't know, I could just draw this. Like, let's say I'm wrong. Let's say E1, JK, E1 is radially inward, not outward. It's okay, I'm going to find a negative enclosed charge, and I'll interpret that as, oh, well, you know, if I get a negative value for E2, really that's just direction. Right? So that's what I'll do. But point is, your flux is going to be the same because you're going to set up the same kind of Gaussian sphere. It's just not going to, it's now going to be big enough that it lives in region 4, right? And going to have a normal DA1, or DA. Don't have to call it DA1. There's only there's only one surface, so DA is good enough. And so, hold on here. Oh, there we go. That's better. Electric flux through my Gaussian sphere is going to be E4 times 4 pi r squared. Flux does not care which region it's being computed in. It only cares that you're computing in it through a sphere. And then Q enclosed over epsilon naught is equal to what? Now let's think about this. How much charge do I enclose inside my entire Gaussian sphere? Well, you might say, well, there's Q, so there's that. And you could argue, well, that's it, we're done. Because Q net on the shell is 0 anyway. And that's fine, right? You could say, well, it's Q plus Q net, but Q net is 0, so done, it's just Q. True. If you don't think about or you don't realize that, you're welcome to argue that I have Q inner here, which is minus Q, and then Q outer here, which is plus Q, and then you'll come to the same conclusion as you can add them to Q if you want, but it's not going to matter because they're going to cancel each other out. So it's just going to be Q over epsilon naught at the end of the day. And so by Gauss's law, E4 there we go, times 4 pi r squared is Q over epsilon naught. I shouldn't be too surprised with what I find, because effectively this is basically a big point charge, right? Once I'm outside of the shell, it looks like a big point charge. And so E4 should be no different than the electric field created by a point charge Q. So that's Q over 4 pi epsilon naught r squared for r greater than or equal to C. If I want to add direction, I will say E4 as a vector is radially outward. And there we go. And just to go back to what I had hinted at earlier, let's say I didn't realize, let's say in fact I didn't know that E4 was outward, and maybe it's inward, okay? Well, then I'd get this, but then I'd get a negative Q enclosed to match it, and that minus would then apply to r hat and tell me that E is radially inward. So I could course correct, even if I guessed wrong about the direction of E4 initially. But so that's how you would go about finding the electric field in each region if you have spherical symmetry. Okay. So what we did here is we did two extremely classic problems. They're so classic that it's not even funny. And there's a good chance you're going to see some version of them, possibly even in lecture, hopefully in discussion, because they're so classic that you need to address them. But worst case, then here you have them. I would know how to do both. I would be comfortable with both. Whether you have Borel or Speleo doesn't matter. These are problems that you're going to encounter in both cases, and of course they involve skills that even if the problems that you get are somewhat different than the ones we did, there's no way that you can go through the class without knowing how to apply Gauss's law for cylindrical symmetry, like we did here, and then spherical symmetry, like we did here. So, super important, worth spending time on, and again, once you get Gauss's law, you're going to really like it because it's super easy to get the electric field from it. It sure as hell is easier than slice and dice, no question. But of course, the price that we have to pay is that we need a lot of symmetry. So it's not true that you can just whip out Gauss's law anytime to find the electric field. You have to have certain symmetries for it to apply. But when you can apply it, it is a lot faster and a lot nicer. So make sure you spend some time on that because it's going to be very useful for the next 2-3 weeks. We'll see that even though we won't be focusing on Gauss's law proper, it will still show up because it will be very common to have, charge distributions, in other words, charged objects that have cylindrical symmetry or spherical symmetry. And even though we might move on to electric potential, we'll see that knowing how to find the electric field is helpful because from there we can find the electric potential. But not to get ahead of ourselves, that is for next week. Let's, keep some fun for next week. And this is really all I wanted to touch on today. Hopefully that helps clarify some of the questions that you've had about Gauss's law. I know that I didn't explicitly address some of the questions that I got, but I figured that hopefully these problems do answer them. So you know who you are. If you asked me about Gauss's law already and you were confused, if this doesn't clear it up, let me know. But based on the questions that you sent me and the problems that I did, I hope it does clear it up. That was part of the goal anyway. So anyway, as always, thanks for watching. Thanks for asking questions. If you need help with physics, feel free to reach out. I'm always happy to at least chat and try to put you on the right track. And if you need more help, like tutoring or masterclass or whatever, that's also an option. And I'm happy to help you through Physics AB so that you only have to take it once. You don't do it as a post-bac, and you can go do the things you really want to do in life, which for most, if not all of you, is not physics. Although I do have stories of a couple of students that were going to go to med school and got pretty far down there and decided they were going to pivot and become a patent patent lawyer, of all things, in tech. So it does happen, but I also am cognizant of the fact that for most of you, 8B is just the last hoop of a painful series of hoops before you can actually, go be a pre-med or a pre-dental student for real. So anyway, thanks again. I'll talk to you soon. See you next week.